Hello, this is Gus from 3DeepLearner.com, and this is the third video in our SIGGRAPH 2018 series. SIGGRAPH is coming up next week, and this is going to be the final video I'm doing, and I'm covering this paper called DeepMimic, an example guide, deep reinforcement learning of physics-based character skills. So this is a paper that focuses on character control from a different perspective. In the last video, I talked about mode adaptive neural networks, which was also focused on character control, but it had a kinematic approach. And now and it also used supervised learning, okay, which is supervised learning, which is what we have been doing so far in this blog. But DeepMimic uses deep reinforcement learning, which we're going to talk about today, and it concerns physically based characters, which is different as well. So what's the difference between these dynamic characters and these other kinematic characters? So we say kinematics is the study of motion without consideration for its causes, and dynamics is the opposite, is the study of motion with consideration to its causes. So for example, if I'm doing machine learning, character control with kinematics, I want to extract character poses, get the rotation of each of these characters' joints, with respect to some input that would be like a trajectory, okay? And in dynamics, I don't care so much as to what's the position and orientation of these joints, but I care as to what are the forces that are being applied to these joints. So for example, there's gravity, and there is these joints, each one has a mass, and maybe the constraints between each of these joints are applying some force, some torque like this, and so on. So here there's a physically simulated environment, and we want to learn forces to control this environment instead of just learning the poses. Okay, so we're trying to learn is, okay, here is without consideration. What we want to learn in a kinematic environment is poses from user input. And in a dynamic environment, we want to learn forces from a user input, maybe, but also from an environment. And an environment can constituted of many things, like the forces, if there's wind, gravity, and so on and so forth, and maybe collisions, something's colliding against our character, and also, maybe other characteristics like the friction and so on and so forth. So friction, okay. So the variations in the environment are kind of infinite, and that makes supervised learning a bit complex. Okay, so that's why we use reinforcement learning. But what are the advantages of this approach? Well, the clearest advantage is that the character becomes a lot more susceptible to variations. So you could throw something at it and it can react to it, and makes the animation more dynamic, as we see in this example. Okay, but the clear disadvantage is that there's a lot more to learn, because the environment can be infinitely varied. So instead of doing supervised learning, which is what we have been doing so far, we need to do, if you want to learn character in this more dynamic environment, we need to do reinforcement learning. And here's why. In supervised learning, we know the inputs and outputs. Okay, so, and we know their relation. So for example, I know in the last video, when we talked about the the MN model, if we had a certain trajectory as input, we knew what output pose we wanted from that trajectory. We knew that this was baked into our data set, and we could tell the model to learn the relation between inputs and outputs. But in reinforcement learning, we could have any set of random variations in the inputs, and we don't actually know what we want as outputs. I mean, sure, we know what pose we want the character to be in, but the outputs of the model are not the poses, but actually the forces that should be applied in each of these joints so that the character gets into that pose. So it's not the same thing. So these are unknown. Okay. What we do know is the goal. So the goal would be, for the character to stand up straight or to walk or to, reach a certain pose and so on. So we know the goal and we can tell the distance from the outputs to this goal. And that's kind of the intuition of how reinforcement learning works. So instead of telling the model the correct answer, we try a bunch of different things, a bunch of different inputs and outputs, measure how far those inputs and how far the outputs actually are from our goal, and if they're directing us toward this goal, then that's something we want to learn. Okay, so I have created a little example in Maya. It's much simpler than what is in this paper. It's just a bob bag character, and it doesn't know anything about life. It doesn't know how to defend himself. So if he's attacked by a bunch of cubes like this, it just dies. Okay, so I then trained a reinforcement model on him so he can learn how to stand up. If you want to check out this example, I'm gonna have a post about it linked under the description for this video. Okay, so what I want to show right here is that although I don't have the inputs and outputs for it, I can at any time evaluate how far it is from the goal. So the goal is to stand up straight, like this joint right here. So I have a function that I have created, which is called getReward. And if I call it, you see that right now I have a very high reward. So it's very close to the goal. And if I go further in time, and it falls like this, the reward is gonna drop severely. Okay? So it's dropping, then it should drop some more. Okay. So this is how we know this is not the right answer. Okay? The previous one, that was much better. So we know kind of the distance to the place we want to go. I'm gonna try to explain this a bit more in depth. So imagine this circle are all the possible human actions. Okay, so let me just get another color of pen right here. Let's say you would have something like all the possible walks in here, walks, and all the possible runs right here, then all the possible jumps here. Okay, and then in this large space right here, you would have your character falling down, probably in a very, very silly manner. Okay, so what we try to do in reinforcement learning, since we don't actually know these boundaries beforehand, we need to learn them, is we throw random samples at first. So let's say we throw one sample right here and one right here and one right here and so on. So this, if you were just to throw as many random examples needed to eventually reach one of these states, that would be very, very hard to do. So we don't just throw random samples. Okay, so what we do is we throw one random state, and then we try to throw a series of different samples around this first initial one. So let's say we throw another sample right here, another one right here, another one right here, another one right here, and so on. And then we get the reward, just as I did in the bob bag character that I showed you. and I get the reward for this one, get the reward for this one, this one, this, and so on. And and then I measure which ones of those are closer to the goal, which could, let's say, be walking. So these ones are clearly better than these other ones. So I could discard these ones and learn the things that get me going in this direction. So I could go and throw another sample right here. And then I will do the same thing. I would throw random samples in this area and separate the ones that get me in the right direction, remove the others, and learn in that direction. And then I could, this would not be a very straight line. I could take some awkward paths like this, but eventually I could reach my objective, okay? So that's the idea. So instead of having one training, like we do in supervised learning, we have many trainings, okay? So we start random, we get rewards, and we train. And then we do that once again, and do that once again, until we are sufficiently close to our goal. Okay, so this is the main idea behind reinforcement learning. Now, your goal can define how your animation will look. So this is a animation from Google's company called DeepMimic, and they're very famous for their reinforcement learning models. And in here, this character learned how to walk by itself, and his only goal is to, move forward and not touch the obstacles. So it's very impressive that it learns to move by itself. It learns how to walk and, move his arms and everything, but it doesn't look very human. Although it's technically impressive, it's not very usable from a character control standpoint. So the main differentiator of the DeepMimic paper is that they not only give the character a goal, but like walking forward, but they also give it a second goal, which is mimic a mocap clip. And that's why the movements look so human-like. So let's talk a bit more about the implementation, the actual implementation for this paper. So this paper, it uses two neural networks. They're very similar to what we have seen before. They're fully connected neural networks. One is called the policy network, and the other one is called the value network. Okay, so we're gonna see that reinforcement learning, it has its own terms and lingo. So I'm gonna try to get you acquainted with that. So for example, the inputs, they have a special name. Okay, it's the state of the environment. And the outputs, they are called the actions. Okay, and the thing that gets actions from given states, they're called the policy. So that's why this is called the policy network. Okay, the state for this paper is determined by the position of each one of the joints, the orientation, the linear velocity, and the angular velocity. And the outputs are the torque, I don't know how to pronounce that, torque, of each one of these joints. So, like the angular force that the joint is supposed to do to reach a certain goal. And the actual paper, it uses something a bit more sophisticated called the partial derivative controller, but you can think about this as just angular speed or angular force for these joints. So we have seen that neural networks are randomly initiated. So we could expect that given a state, we're going to get a random action. But as I told you, we don't want just a random action. We want the random action and the actions surrounding it. Okay. So what is actually done is that we not only get these actions, but we randomize them a little bit, just a bit, so we can get different perspectives of this action. And each one of these random samples is going to get a reward, okay, based on how good it is, how far it is from our goal. So let's say we could throw one initial sample and the reward would be 0.5. Okay, and then we throw another sample and the reward would be 0.6. Okay, but how do we know that this 0.6 is better than 0.5? For that, we use this second network called the value network. So what the value network does is that it learns what is the reward for any given state. So for example, if we throw this first sample I talked about, we would then use this to feed the value network, and the value network would learn that this state gives us a 0.5 reward. And then the next time we try to input this state to the network, and it would randomize the action a little bit, and we get 0.6, we know that this is better than what we previously had. Okay, so there is an advantage to this new randomized sample. So we would say that the reward minus the value is the advantage. Okay, so this behavior has an advantage to previous behaviors. So that's how the network actually learns. So we run a bunch of simulations, get a bunch of actions from states, and then we train the value network with the rewards from those actions. The next time we train the network, we will randomize things a little bit, and if we perceive an advantage, if there is reward that is greater than the values, the rewards that preceded it, we're gonna have something that is worth using to train the policy network. So we will only train the policy network with advantageous samples. Okay, so the loss function for this network, it's kind of like the mean squared error, but the error is multiplied by the advantages. So we only minimize those errors that are advantageous to us. Okay, so then you gotta do, rinse and repeat this operation many times. So in the original paper, the samples used to learn one simple skill, or none of those skills are actually simple, they're very complex, but just one skill is has 6 million, okay, 6 million samples. Okay, because not all samples are going to be advantageous, many are going to be thrown out, and so on. So it's a very slow process of learning. Okay, this example that I did in Maya, it is much simpler. We only have one joint, so it's a lot easier to learn. And I have learned the whole behavior in like 8 training sessions. So each training session had about 1,000 samples, so about 8,000 samples. Okay, so this, for example, is the model with only 2 training sessions. It doesn't know much about how to stand up for itself. And then at 4 training sessions, it's a lot better. It takes a while to get back, but it does. And this is the model after 8 sessions. Okay, so we can see right here, if we click in the model and check out its attributes, that it is applying a force here in this torque impulse parameter. Okay, and this force varies depending on the angle of the object in relation to the reference. Okay, so right here, the reward is basically the distance in velocity to this object, to this reference object, and the distance in orientation. Okay, so Both of these are used in the paper, but the paper also has more rewards it calculates. So these are the rewards for the skills, okay, for learning the basic skills. So it's distance to the reference joint orientations, distance to reference joint velocities, distance to reference effector positions, and distance to the reference center of gravity positions. But the model can also learn new tasks. So for example, we could use the distance of like the hand or the feet to a target to make the character hit a target. So this is one of the great things about the reinforcement learning, is that not only you can have the original motion, but you can change it a bit to not only react to environment, but to alter its goal. So this paper kind of proved that this is possible, and it looks really good. The movement looks very human-like. Okay, so I hope this was enough to give you a basic idea of this paper. There's a lot of details that I had to omit because it's no pun intended, it's a very deep paper, and it shows a lot of different applications of the model. So let's just discuss the main contributions of the paper. So in comparison to previous reinforcement learning models, the movements are very human-like, okay? So this is very positive. Human-like movements. They don't look like something that the computer learned by itself and it's funny. In comparison to papers that rely only on kinematic approaches, it reacts to environment, which is great. Reacts to environment. And it can change a base action, like we have seen with the kicks in the previous slide. It can change a base action. Change base action according to a goal, which is great because we could have only one motion capture and, you know, have several different movements from it. I guess the main drawback of this paper or this reinforcement approach is the long learning process. Okay, so long learning process. There is a lot of random samples that are thrown, and much of it is discarded, and just a fraction of that is used for actual learning. Also, there is a lot of variation in the training process, but the authors, they overcome that with techniques that are explained in the paper, although I haven't discussed them in detail in this presentation. Well, so this example that I showed you in Maya, you can see it in the description for this video. I have the link. You can play with it. You can train your own model. So please experiment with it. Well, guys, this is the end of our SIGGRAPH series. I hope you really liked it. This was really fun to make. I have learned a lot, and if this has been valuable to you, please share our links in your social media and share it with your colleagues. Thank you very much. Until next time.